1997 E&M problem 2. They give us a non-conducting sphere, and they are very nice in telling us that it is a spherically symmetric electric charge. That's usually an indication that they're going to change things on us later on, and when you get down to parts D, E, and F, they do. And we're going to look at the electric field at point P, which is on the right side. It is a specific point on the right side of the sphere. So for part A, to get the electric field at point P, it will be most straightforward and also algebraically the easiest if we just use Gauss's law. And that's supposed to be a dot there. All right, the Q enclosed is going to be all of it here outside the charge. And since they tell us sphere twice, non-conducting sphere and then spherically symmetric. That means we can use the surface area of a sphere for that dotted line that is enclosed. So substituting both of those guys into our Gauss's law expression above gets us 1 over 4 pi epsilon naught q over r squared. And since they say specifically that they want to know what the electric field is at point P, and the electric field is a vector, we need to include the direction to the right. Or if you want to draw an axis system with an x and a y, you could say I hat. But I just said to the right on my answer because I think that's sufficiently clear. And if anything, it might even be more clear than using I hat. All right, part B. The flux of the electric field through the whole surface centered at C. Well, Gauss's law, as written here, ignores an important piece in the middle. That is, the charge enclosed in a surface produces electric flux through that surface, which is then measured by the electric field spread out over the entire area. So for part B, we could either look at the left side and say the enclosed charge over epsilon naught gives us the flux, or we can look at the right side and say the electric field times that surface area, and they tell us it's capital R, so this guy should be capital R squared, and either one will be sufficient because they do say the flux of the electric field. That's an indication that we should be allowed to use E in our answer, but because it's produced by the charge, we can also use Q. So either one of these would be fine. I would pick the one on the left simply because capital Q right here, capital Q is an actual given and E is not. Part C. Point particle negative Q is now place distance. Determine the magnitude and direction of the electric field at point P. Okay, so now we have a sphere of charge, which as soon as we're outside of it, it might as well just be a point charge. And it's going to produce an electric field to the right. So that's going to be E plus. And this minus charge is going to produce an electric field down. And those arrows should not be rotated like that. Let's see if I can draw better. All right, so there's electric field to the right. And there's electric field down. So here's E from the plus, and here's E from the minus. And since this distance is R and this distance is R, and this is a Q and this is a Q, if we take a look back at A, we have 1 over 4 pi epsilon naught Q over R squared, and the R's are the same and the Q's are the same, which means that the overall size of these two vectors is the same. So that means the sum total of those two vectors is going to be down and to the right at 45 degrees. So what that means is that we have to add these two vectors together like they are the sides of a right triangle. And we're going to have E total is going to be E plus in the x direction plus E minus in the minus j direction. Now, they only want the magnitude. Oh, wait, nope, they want magnitude and direction. Okay, so we're going to square this guy and square this guy and add them together and then take the square root. So squaring these guys, adding them together, and taking the square root gets us 1 over 4 pi epsilon naught q square root of 2 over r squared down right at 45 degrees from horizontal. We need to make sure that we include not just 45 degrees, but 45 degrees from where? So if we come back here, that'll be 45 degrees from the horizontal. If you want to be tricky and say 45 degrees from the vertical, it's the same thing, so yes, you could say that. All right, part D. And I think I'm going to have to clear all this out for parts D, E, and F. Okay, part D. Now we're going to zoom out and say, well, you know what? There are actually 4 charges floating around here. Let's enclose charges 2 and 3 in a bubble, and we'll put P1, not P, P1, on the surface of that bubble. Which of these charges contribute to the net electric flux through the surface? Okay, so 1 and 4 are both outside. So if we draw an electric field line from, oh, I need to have a pen. If we draw an electric field line from 1, just in an arbitrary direction, we can see that on the left side of the surface, the field line goes in, and on the right side, that line comes back out. So the net flux from Q1 across this surface is 0 because we go in and then come out, and there's no net flux from Q1. And the same thing will happen with Q4. Contrast that with, let's choose Q3. Q3, when we draw an electric field line that starts on Q3 and then goes away from Q3, notice I'm assuming that they're all positive charges. It doesn't really matter if they are or if some are plus and some are minus. We'll just use the individual ones. So this just goes out of the surface. There's no corresponding from Q3, no corresponding electric field arrow that goes in. So 2 and 3, so D1, Q2, and Q3 contribute to the net electric flux through the surface because they are enclosed by the surface. All right, now part 2. Which of these charges contribute to the electric field at P1? Okay, so at P1, we're going to have an electric field from Q1 in that direction, from Q2 also in that direction, from Q3 up like that, and from Q4 in that direction. And we can just add these guys vector-wise like we did in part C with the 2 charges, the plus Q and the minus Q in part C. The electric field is just the vector sum of the individual fields. So for part 2, it will be all of them. And for 3, we would then say our answers are different. Our answers are different because the electric field is the vector sum. So we can say the E field is vector sum from individual charges. But the flux is sum over a whole surface. So over that whole surface, you have to account for the fact that Q1 has an in, which would be minus, and an out, which would be plus. And those 2 guys are going to cancel each other because every line that goes into that surface is then going to exit that surface on the other side. Part E. if the net charge enclosed by a surface is 0, does that mean the field is 0 at all points? Well, no. What if we say that Q2 is plus and Q1 is minus, and they're the same size? So we have a proton and electron. They're the same size electrically. So that means over here we have electric field lines exiting, and then over here we have electric field lines entering. And for some of them we would have exit and enter as it goes from the plus to the minus. So overall we have 1, 2, 3, 4, 5 field lines leaving the surface, and then 1, 2, 3, 4, 5 field lines entering the surface. So the net charge is 0, and the flux is 0, but the electric field, if you are going to be taking a look at the position of Q1, you're closer to the positive charge, so you're going to feel an electric field pushing you away from that positive charge. So part E, the E field is not 0 at all points if the charge distribution is asymmetric. That's an R. F. If the field is 0 at all points, does that mean that there is no net charge? Okay, well, let's back up here and say, let's bring these guys, let's go back up to our picture from right above part C. The field is 0 at all points, so we've got 0, 0, 0, 0, 0 all over the place. In order to get 0 electric field, that means inside we have to have 0 net charge. Remember our Gauss's law equation, Q enclosed over some constant produces flux, which can be broken down to the electric field being spread over the area. So if this guy is 0 on this side of the equal sign, then that means this guy is 0 in the middle, and that means this guy is 0 on the left side of the equal sign. So if E equals 0 across surface, Q enclosed has to be 0 as well.